morning, everyone. Thank you for joining this keynote today. I'm Yang Seok-ki, a Senior Director of Memory Solutions Lab of Samsung Electronics at San Jose. In this keynote, I will be talking about power-efficient data processing with software-defined computational storage. Especially, I'm excited to share Samsung's vision for computational storage with industry. Here is the outline of the keynote. First, let me overview how data gravity has transformed IT infrastructure to be data-centric. Next, I will explain why computational storage is a suitable technology for power-efficient data processing. Then I will explain what R&D activities Samsung has been doing in this field and what products we are preparing. Finally, I will conclude by introducing how to create new value constellations through open innovation. First, let's talk about data gravity and how it has influenced data processing technologies. As cloud technology becomes more common, enterprise IT infrastructure is rapidly changing to be cloud-friendly and gradually transform into a hybrid cloud. As a result, hardware and software resources can be easily obtained in a form of services across corporate boundaries whenever needed. In addition, since the advent of the cloud, a large amount of data in various forms is being generated at high speed. Big data technology capable of efficiently storing and processing such data is being developed and disseminated. In addition, artificial intelligence technology has made remarkable progress in the past decade. Especially, machine learning technology has made it possible to extract valuable information from massive raw data accumulated by cloud and big data technologies. What we notice in this trend is most of these technologies are open source and have created healthy and rich communities. As a result, data storage and processing technologies have been democratized. Furthermore, the democratization of analytics technology has made the technology even more scalable and created bigger market. Due to these disruptive changes in the IT environment, large amount of data has been easily produced and consumed. And the enormous of data we never have seen before has created a new phenomenon. In 2010, David McCrory introduced the concept of data gravity. He creatively defined the mass for data and application. Simply put, application has a small mass because the amount of data that the application can process at a time is limited. So the application is inevitably pulled by the gravity created by the massive data. This means that moving computation is easier than moving data. He also defined a force formula for data gravity similar to Newton's gravity. As I/O latency and throughput requirements increase, gravity gets stronger because the time for data transfer gets shorter. In order to speed up data transfer times, an application or service gets closer and closer to the data. Data gravity is rapidly accelerated due to M&A, cyber physical system, data localization, etc. In addition, the policy of public cloud providers that high prices are charged for outgoing traffic makes it harder to move out data from cloud. this consequently accelerates data gravity. So how is data gravity changing the IT landscape? Let's revisit the paradigm of large-scale data processing. Before the cloud era, data warehouses were popular for large-scale data analytics, such as decision support and business intelligence applications. Data warehouse separate data processing from data collection and processes structured data through ETL operations. ETL here represent extract, transform, and load. Since the advent of the cloud, a large amount of unstructured data, semi-structured data, as well as structured data has been generated. Data lake technology has been developed to store data for many different analytics products and workload. Each application determines how the data is processed when an application loads data. For this reason, data lake does not have some critical features for data processing, such as transaction, schema, consistency, isolation. So it is almost impossible to mix jobs with different characteristics. As you know, data warehouse is not designed to optimize large volumes of unstructured data. In contrast, data lakes are not designed for data management or processing. As a result, a common practice to handle big data is to use multiple systems, including a data lake, several data warehouses, and other specialized systems. Having many diverse systems introduce complexity and introduce delay due to move or copy of data between different systems. Recently, Data Lakehouse is emerging as a platform that can effectively perform various data processing and various data storage together. Data Lakehouse is enabled by open and standardized system design. It still takes advantage of flexible storage that the data lake provides, but data is managed in a more organized way and processed as is done in data warehouse. In summary, data gravity influences the landscape of large-scale data analytics systems, which are evolving centered around large-scale stored data. So what is the impact of these macro trends on the underlying hardware IT infrastructure? In particular, how can the storage industry respond to customers' needs better? The macro trends are based on advances in the hardware and the computer architecture that can underpin the technologies. In the past, when the amount of data was not large, CPU scale-up was a major interest. During the period when Dennard scaling and Moore's law are applied, computational power can be doubled every 18 months, while keeping the electric power consumption constant. However, since mid-2000, Dennard scaling is no longer effective due to the power wall caused by leakage current and threshold voltage. And the Moore's law also takes longer to increase transistor density. As an alternative, a scale-out approach based on network technology was proposed in early 2000. Google File System is the most notable technology that has solved the big data problem very well based on scale-out technology and the data gravity. Although the scale-out solution made a great contribution to solving large-scale problems economically, a lot of power consumption and increased network costs were considered as problem as the systems grow. Here, the scaling solutions come into the picture to improve the overall TCO. In particular, we need to pay attention to domain-specific computing architectures, as Professor John Hennessy has emphasized. Even though it is arguable, according to Huang's law, the number of transistors in GPU is increasing at faster rate than the Moore's law. We noticed that one of the major architectural issues that drove this paradigm shift is electric power. These days, various types of domain-specific architectures are really booming, especially in the AI domain and the network domain. At least, domain-specific architectures still enjoy theories for CPU's early glories. Let's take a closer look at domain-specific computing architectures from data state perspective. According to its state, data can be classified into data at rest, data in transit, and data in use. In the past, CPU were used universally regardless of data state. However, now there are many domain-specific architectures that can efficiently process the data in each state. The domain-specific architecture is purpose-built for power-efficient and high-performance data processing. First, data in use usually refers to data residing in volatile memory, and the various MPU, including GPU and TPU, utilize memory hierarchy to process compute-intensive data efficiently. On the other end, data in transit refers to data moving through the network. Smart NIC, DPU, smart switch, etc. can effectively process network acceleration functions such as packet processing, protocol processing, and the storage network functions. Finally, data at rest refers to persistent data residing on storage devices. Computational storage can effectively handle data transformation and the filtering function while data is stored to or retrieved from storage. What these technologies have in common is that they move functions to the device, which matches the intrinsic capabilities of the device and is more optimized than how CPU processes them. Then, is computational storage the best domain-specific architecture for technology trend of data processing driven by the data gravity? What is the potential benefit of computational storage device? One of the most important resources in today's data center is electric power. If a technology could be efficient from a performance per watt per dollar standpoint, such technology would be very interesting. Most computational storage devices employ low-power embedded CPUs or ASIC-based computing units. So computational storage can save power consumption of the system as a whole, not just the CPU, because it allows the system to be idle while performing computation. Second, computational storage can significantly reduce the amount of data traversing the system because only filtered or refined data leaves the storage after it has been processed. This means that the system uses less electric power for DMA and the I/O bus is less congested. This can also improve CPU cache performance and network utilization because of less footprint. Third, the high total internal bandwidth of the storage device has the potential for high data processing throughput. The data bandwidth inside the storage device is usually greater than the interface bandwidth. And the actual storage bandwidth available to application is limited by PCI bus or network bandwidth. Therefore, it can be said that the total internal bandwidth across devices as a whole is greater than total I/O bandwidth available on the system. If total internal bandwidth of these devices can be utilized, the system can deliver much higher throughput at little additional cost. Last but not least, as more devices are added, the overall computing power increases proportionally. Again, the actual storage bandwidth available to application is limited by PCI bus or network bandwidth. For this reason, a large number of storage devices in a storage system mostly contribute to increasing storage capacity, but is limited in contribution to bandwidth or computing power. In the meantime, the functions of computational storage can be classified into two types based on purpose. One is offloading, which is mainly aimed at reducing CPU load. And the other is acceleration, which performs computation better than CPU. Offloading is mainly done for background or offline tasks with less electric power and weak real-time requirement. On the other hand, acceleration mainly focused on improving performance of foreground or online tasks with a strong real-time requirement. In summary, computational storage is a technology that exploits the potential benefit of low power in situ processing for data refinement and management. To realize the potential benefits of computational storage, Samsung has been paying attention and investing in computational storage for nearly a decade. Let me introduce Samsung's R&D activities. Especially, I will introduce our current and the future product as well. Inspired by active disk research from CMU in the late 1990s, Samsung became interested in SSD-based computational storage and started a pilot research project in 2011. As you can see, SSD is a complete small server with a CPU, DRAM, NAND, and fabric interface. To leverage high internal bandwidth and low power ARM processors using SSD, several use case studies on data filtering acceleration were conducted. This includes scan and join operation of relational database and the Google PageRank operations of web search engine. One of the lessons from the series of studies that the embedded CPU used in SSD have limited computing power, limiting application, and making business difficult. In other words, in terms of cycle per byte, SSD cores are on order of magnitude slower than host cores, and SSD has much fewer cores than host CPUs. For this reason, we developed another SSD with a simple hardware scan IP on the controller responsible for NAND I/O to improve computing performance. This hardware engine performed high-speed pre-filtering at a line rate for each page. As a result, the performance of TPCH top 5 queries improved by 15 times on average. When the scan occurs, SSD utilization and instantaneous electric power increased. However, the execution time was significantly reduced. For example, the total energy consumption of TPCH query 2 is reduced by 24 times. After several years studies, Samsung launched Smart SSD, the first commercial computational storage product from Samsung, in 2020. Smart SSD is a platform for cost-effective and scalable data processing. Let's take a closer look at its architecture. Based on PCI Gen 3, the Smart SSD offers 4 TB of storage capacity and 4 GB device memory space in a U2 form factor. It also adopts FPGA to increase computing power and application flexibility. The FPGA provides around 300K lookup table to implement custom IPs. There is also a special PCI lightweight bridge implemented in FPGA. This bridge allows a single device to be used as both an NVMe device and an FPGA accelerator simultaneously. In particular, the bridge plays a very important role in data transfer. The FPGA can communicate directly with SSD without host intervention once the source and the destination are set by the host. This can remove a potential bottleneck on the host PCI bus and enable scalable computing with more devices. In order to see how computational storage devices improve TCO, we have worked with several startup companies and applied this device to a variety of applications and systems. First, we implemented a video transcoder on Smart SSD. A video conference application was evaluated in a real customer environment using CTXL's implementation of H.264 codec. As you can see, CPU utilization has decreased by 23% and performance is improved by 80% compared to the existing system. Smart SSD also been applied to cyber forensic application in collaboration with Luis Rowe's lab. When identity theft occurs, you need to scan the entire storage to see what has been compromised. Smart SSD has a scan done in just 25 minutes, while the current system takes several orders of magnitude longer. One important observation is scan times are nearly constant regardless of storage capacity, as scan can be performed independently on each device in parallel. Meanwhile, Smart SSD was applied to file system as well. IDT-COM's no-load file system automatically compresses data as files are stored. The no-load file system was implemented using Smart SSD. And a relational database using this file system was able to save more than 3 times storage spaces without performance degradation. Finally, we apply Smart SSD to a relational database. Swarm64 is a PostgreSQL solution that supports columnar store using column index. Swarm64 implements a scan engine on Smart SSD and allows users to achieve comparable performance at 1/3 the price of Amazon Redshift or Postgres. As seen in video transcoding and cyber forensic examples, it is important to note that computational storage device increases its computing power linearly as the number of devices increases. In other words, as storage capacity increases, computing power naturally increases as well. As a result, computational storage can reduce the number of servers and thus improve the overall system TCO. Today, in this keynote, I'm going to share Samsung's direction for next generation of computational storage products. As mentioned earlier, research project and Smart SSD primarily focus on key mechanisms, use cases, and TCO. The most important lesson from a series of studies and product effort is that we need friends to travel with to make technology successful and scalable. Our next generation device is focusing on developing a platform that enables various collaborations and technologies. The platform is built on two main design concepts. The one is bring your own IP, and the other is software defined. The bring your own IP concept will expand hardware capabilities through collaboration and make computational storage features rich. On the other hand, the software-defined concept makes it easy for users to use this device and for software engineers to expand the device functions. Based on these two design concepts, next generation device will be made comparable but competitive. The device supports standards such as NVMe TP4091 and the SNIA Computational Storage API. We also plan to release a software development kit later this year that includes a library that is compatible with SNIA Computational Storage API and a device driver that is compatible with NVMe TP4091. On the other hand, security and the multi-tenancy in the cloud are known, and device will have several system-level security features, including advanced encryption standard. Finally, one of the most challenging issues with computational storage is to handle different data formats in terms of data organization, compression, encryption, and so on. Not all formats can be supported very efficiently, but this device accelerates some popular formats. We consider the next generation device as a hardware-software co-design platform for in-storage compute. We expect that our next generation device can support various hardware IPs. The compute module here in the next generation computational storage is a hardware component for various hardware IPs. The compute module consists of embedded CPUs and IP cores. The embedded CPUs can perform functions that CPU can handle well, such as management and complex control planes, while the IP cores implement the compute function that require performance. For example, NVMe TP4091 proposal defines more than 10 potential operations that our computational storage can support, such as compression, encryption, filtering, checksum, and so on. In addition to the basic IP cores provided by Samsung, this compute module can accommodate custom IPs from third-party for business cases. In other words, we are open to customize the device design through concept of bring your own IP with partners. We also hope that this computational storage device will be connected with various technologies around it, such as DPU, GPU, via fabric protocols such as NVMe, NVMe Fabric, etc. We believe that collaboration, even with competing technologies, can enable more flexible computing environment and provide more option and a better TCO to the customers. Next, let's look at the device from a software point of view. For end users, our next generation device will introduce the concept of end user computing. Regardless of hardware capabilities, we want to make it easy for users to use the capabilities of SSD. In other words, it aims to provide high-level services or APIs for use by end user in the form of pre-built or custom containers. For example, data scientists should be able to use filter operation in computational storage by using only SQL without needing to know how underlying mechanism works. This is similar to software as a service concept in cloud. Next, the environment and capability of a host and device can be created and defined through containers. Application software engineers can use standard library-like APIs in their applications after the appropriate container are set up. These libraries can be provided by Samsung or community in the form of pre-built container or custom container. This is similar to platform as a service concept in cloud. Or infrastructure developers can implement their own function based on NVMe Computational Storage Standard or SNIA Computational Storage API. They can implement the function in the form of a custom container. For example, infrastructure software engineers can develop new device functions using eBPF, download and execute the program using SNIA Computational Storage API, and NVMe TP4091 commands. This is similar to infrastructure as a service concept in cloud. This platform offers different level of development options, and the user can define the capability of SSD to suit their needs. I hope you have some excitement and see opportunities our next generation computational storage device. Now, let's talk about how to create value constellation to grow together. Computational storage device is still in its infant stage. And we still have many challenges from both a business perspective and a technology perspective. First of all, we need more use cases and strong TCO benefit should be able to demonstrate. In addition, technology must be mature enough so the customer can easily adopt the technology without incurring high acquisition and engineering costs. Meanwhile, various technical issues must be also addressed. We have software ecosystem issues such as virtualization, multi-device data consistency, and also have device architecture issues such as security, multi-tenancy, device interface performance. In addition, we need to deal with various data characteristics issues such as data type, format, compression, encryption, etc. We believe that this is not a problem that one company can solve, but a problem that community must solve together. Academia will be able to develop more technologies and use cases not covered by the industry, and to lay the groundwork for technology and evangelize technology through the papers. Partner can deliver practical and commercial solutions through vertical collaboration in a form that end user can consume. In addition, competitors can work together through horizontal collaborations to create a software ecosystem that is compatible with each other to fuse multiple technologies. As seen in the case of smart SSD collaboration, Samsung has introduced several solutions through vertical collaboration. We develop solutions that enables end users to consume smart SSD together with Bigstream, IDT.com, Swarm64 through open source software such as Spark SQL and PostgreSQL. In addition, we are providing a way to increase access to devices and perform various evaluation by providing smart SSD as an infrastructure as a service through Nimbix. However, The applications mentioned here are only a few of applications that computational storage device can contribute to. And it is expected that more applications that end user can consume will be provided. We hope to see your company's logos here through bring your own IP or software-defined solutions. In order to effectively handle large amount of data, it is necessary to take the best technique for given data across its state. Samsung further suggests horizontal collaboration to address this problem. Intuitively, computational storage is the best for pre-processing stored data. This can reduce the amount of data to be transferred from storage and consequently increase the effectiveness of the data. For example, we can use Spark's map operation in a computational storage device to perform simple filtering operations. In an environment that DPU or SmartNIC manage multiple computational storage devices, we can handle the pre-processed data from storage devices. For example, they can perform aggregate operation over partial data that each storage device generates. Or they can conduct data distribution like shuffling across a cluster system based on data properties such as hash value. For data with a large amount of computation, a device suitable for computation such as CPU or GPU can be utilized. As the data become more active, the volume of data can decrease while computing complex increases. However, the optimal solution depends on the nature of application and data. Therefore, it is necessary to make an effort to perform data processing by utilizing various devices in consideration of application and data characteristics. Also, these solutions must be done through consistent APIs. We believe that open innovation is the best way to make a new technology like computational storage successful and scalable. And multiple value constellations can be created through a vertical collaboration, horizontal collaboration, or both. Samsung wants to grow together through open innovation with partners. Samsung will develop and provide software that meets standards such as NVMe and SCMs. In addition, Samsung plans to develop a reference system and disclose it through a system consortium such as OCP. Finally, we will make our technology accessible through the cloud so that the universities, collaborators, and customers can access and evaluate them. Samsung Electronics is calling for actions to the industry to work together to create new opportunities. We have a separate breakout session for computational storage today. I encourage you to find more technical details about SNIA computational storage architecture and APIs in the section. Again, Samsung is looking forward to working with you. Thank you for your attention. Now, let me take questions.